So hello and welcome to Ask Echometer. Today's session is titled Acoustic Techniques for Gaslift Wells. And I will be presenting today. I'll be talking through the presentation. And we'll have Q&A with Lynn Rowland and, of course, Gustavo. And Gustavo does a great job manning the chat, kind of behind the scenes, too. If Lynn has some comments and things during the presentation, then we certainly want to hear from him as well. So here's our email addresses, everyone at Echometer. Our email address is our first name at echometer.com. And for this presentation today, there are two technical papers that I've got listed on this main screen here. And so both of these technical papers, they're available for download, or if you'd like to, you can even just respond to the invite that I sent to you. If you'd like to have a copy of the papers, I'll be happy to send those to you. So during the session today, we want to cover several of the benefits of shooting fluid levels on gaslift wells. We'll look at several examples, and I've got lots of examples to show you. We're also going to do an introduction to the Dual Shot Acoustic Technique, or the Dual Shot method. I do want to show you, for those of you who are interested in looking at the data, you can look at it along with me, or if you're reviewing this session after the fact, if you go to our website. So here's echometer.com. This is our homepage here. If you click on Ask Echometer, if I scroll down, you can see each one of our weekly sessions that we have out there from our past weeks. And down here at session 5, you have the ability, this is where I'll have the recording for you to watch after the fact. You can also download a copy of the presentation. Right here, if you click on Download TAM Example Files, so I'm going to do that, and it's going to download this folder here, this Ask Echometer Gaslift dataset. So if I open this up, you have 3 files here. So this middle file here is the TAM file that has the Gaslift examples. Down below that, you have a PDF. So this PDF goes along with the Gaslift examples. So each one of the examples there, I wanted to have just a little more information for you. There's 7 examples on here, and I don't know if we'll get to all of them today, but I wanted you to be able to refer back to this document just to give you some things to look at with each example, and then some just additional exercises so that you can exercise those features that we have within the software. Sometimes it's nice just knowing where they are and kind of what they can do. Also with the examples, there is a spreadsheet here, an Excel spreadsheet. So for 2 of the examples, multiple kicks 1 and 2, these are the gaslift valves that are that go along with those examples. And then for the multiple kicks 2, there is a deviation survey. And so I wanted you to be able to practice, if you needed to, practice pulling the deviation survey into TAM, and also practice creating the gaslift well file with the gaslift valve entries, things like that. So we have this information here, and we'll try to get to as many of those as we can today. We had a couple of questions before about the actual data set itself. If you double click on that, you don't even have to have the software open yet. If you double click on the examples folder and open up TAM, so TAM's going to automatically open up and get ready to import that data set into your TAM software. So if you just leave it as it is with this same group as file, you'll see it's going to create an Ask Echometer Gaslift Examples group. So if I click import, and I already have all of mine in there with a couple of notes and things, so I'm going to skip that, but you'll see all of the gaslift examples loading. I think there's a total of 7 wells, and I think 25 fluid level tests and some plunger lift tests in there as well. All right, so I just wanted to make sure you guys knew where that information was located, and I will get back over here to our presentation. All right, so the distance to the fluid level provides beneficial information throughout the life of a gas lift well, from the initial unloading of the well to maintaining production, and even into troubleshooting the well. Using the acoustics, the fluid level shots can play a crucial role in understanding the well's performance. So we can see the fluid level depth with respect to the valve. We see the depth to the deepest mandrel uncovered. You can verify if your unloading process is proceeding properly, find holes and restrictions. We can use the acoustics to determine if you've got a wellbore problem or maybe an equipment malfunction. And we're going to look at several examples of how you can use acoustics to aid in your troubleshooting. So during the initial unloading sequence of a gas lift well, acoustic fluid levels can be used to monitor the unloading process. Some of the most valuable fluid level shots occur when the fluid level is compared to the gas injection depth. So shots down the casing annulus provide a quick look at uncovered mandrels as the annular fluid level is displaced by that high pressure gas injection into the annulus during the unloading process. All right, so once we have a stabilized gas lift well, the annular fluid levels should remain constant with respect to the operating valve. Oscillations of the liquid level depth may indicate valve operation or gas injection rate problems. In a well with a packer, the deepest liquid level indicates the deepest mandrel uncovered from the unloading process. Wellbore integrity problems can be detected, and we'll look at some examples of this. Valve stuck open, leaking packer, leaky check valves. And then during our workover, monitoring the fluid levels of a well filled with kill fluid ensures sufficient hydrostatic pressure is maintained against the formation. All right, so let's look at a fluid level shot here. So this is a shot on a gas lift well. So we see the shot goes off here at 0 seconds. We see some kicks here, so we know we're likely seeing some mandrels, and we have a nice big down kick for the fluid level. So with the TAM software, you're able to go in and actually enter all of your mandrel depths. And so when you turn on your wellbore overlay, and so that wellbore overlay is located in your annotations. If you click that annotations button, and typically it's defaulted to already turn on, but if you don't see it, that's where you can go to turn that on. So that wellbore overlay just gives us a really quick look at where our reflection kicks are lining up with our mandrel locations. All right, so here we can see we've got 10 total gas lift valves entered on this particular well, and we see the fluid levels located right there between the 9th and 10th valve. So that wellbore overlay makes it really easy to identify where that fluid level is with respect to those valves. So one of the things that, this is the same shot here, here you see I have the numbers with each one of those mandrels. But now I have the gas lift valve with respect to, we've got an arrow pointing to each one of the actual reflections. And so if you'll look here, the reflections don't exactly line up with each one of those valves. And that's because the acoustic velocity is changing. And it's very typical to see the acoustic velocity fluctuating along with pressure and temperature, especially as the depth of the well increases. And that's pretty much on any producing well. But being able to see the gas lift valve and its individual reflection all the way down gives us a really good idea of how we can create sort of this a trend, where we see the increasing acoustic velocity. So not all markers line up exactly with their reflections. This is due to the acoustic velocity changing. There's a little bit closer view there. All right, so let's talk a little bit more about the acoustic velocity. So gas lift mandrels are excellent downhole markers. We can accurately calculate the distance to the liquid level, plus any other downhole reflectors, such as the gas lift valves and mandrels, tubing collars, subsurface safety valves, possible holes or other problems. The distance is determined using the echoes from the gas lift valves at known distances from the wellhead. And we're able to account for variations of the acoustic velocity that, again, we commonly see in wellbores due to the variation of temperature, pressure, and also gas composition as a function of depth. So this is kind of a busy slide here, so let me just explain what you're looking at. Here we have the acoustic velocity profile for a gas gravity of about 0.64. So this is the gas gravity of, say, methane. So along the bottom here, you see the pressure increasing to the right. We see the acoustic velocity increasing vertically as we go up the chart here. And then each one of these curves represents temperature, right? So we can see as the pressure increases, we reach to higher temperature curves, then the acoustic velocity increases. So the acoustic velocity depends on the gas gravity and composition, the temperature along the wellbore, as well as the pressure profile. We can determine acoustic velocity using a few different methods, either from counting collars, by using the downhole markers, or by looking at the pressure, temperature, and the gas gravity of the gas. So typically the gas has a uniform composition when the gas is flowing. This right here, if you'll look back over at this graph, this is a wellbore that's been plotted within this graph. And so here at the surface, this is a gas lift well. And so at the surface at 0 feet, we have a temperature of 70 degrees Fahrenheit, and the pressure is 700 psi. So as the depth of the wellbore increases, we see each one of these, we can pretend like possibly these are gas lift mandrels, right? So as the depth of the wellbore increases, we're reaching up to higher temperature curves. All right, so way down here where the fluid level's at 10,200 feet, the temperature is 250 degrees Fahrenheit. We have a pressure of 956 psi. So if we come over here to the left, we see that the acoustic velocity is just over 1,500 feet per second. So the acoustic velocity is incredibly important in making sure that you have an accurately analyzed fluid level shot, and you're going to get an accurate depth to the fluid level. The reason is because typically in gas wells, you don't have collars to count, or in gas lift wells, because of the reflections between the valves and the mandrels, that the reflections kind of overcome any possibility of seeing the individual collars. So the collar count method is not very effective. So we need to use either the acoustic velocity method or a downhole marker. So gas lift mandrels make excellent downhole markers, but it's only going to be effective if we're able to choose the marker that's closest to where the liquid level is. And so this is a really good visualization of that. If you were to choose, just choose that first gas lift mandrel that you see when you're analyzing this shot, the software is going to use the acoustic velocity of 1,300 feet per second to analyze the shot. And it's going to make the assumption that way down there where your fluid level's at is 1,300 feet per second, the acoustic velocity. When in actuality, the acoustic velocity closer to the liquid level is over 1,500 feet per second. So in a shot like this, a fluid level at 10,000 feet, your shot could be 10, 12, 14 seconds. And so if you're off by 200 feet per second on your acoustic velocity, that's going to be a pretty big error in that fluid level calculation. So when you're choosing the marker you want to use as your downhole marker for the fluid level shot calculation, you want to make sure that you're choosing the marker that's closest to where the liquid level's at. That's going to give you your most accurate fluid level calculation. So another thing to remember about acoustic velocity, and we always try to stress this in our schools, it's really good to have at least an idea of what your acoustic velocity should be. If someone calls and they have a problem, they have a particular well, and I ask them what type of gas they have in the well, if they say methane, then I automatically expect to see, when I look at their fluid level shot, I expect to see around 1,400 feet per second. That's just going to be an average. If it's a heavier gas, if they've got, butane or propane, it's going to be closer to 800 feet per second. So knowing the types of gases that you have in the well and knowing the average acoustic velocity to look for, so every time you shoot a fluid level and you analyze that shot, just take a look at that acoustic velocity, because that's going to be an excellent quality check for you every time you shoot a fluid level. That way, if you shoot a fluid level and you've got methane gas and you shoot a fluid level and it just doesn't look right, take a look at the acoustic velocity. If you see an acoustic velocity of 900 feet per second or 736, that's going to be an indication that maybe you've chosen the wrong marker. Something about that shot's a little bit off. You need to go take a look at that analysis. All right, so acoustic velocity is incredibly important. So here we have a Gaslift shot. So which marker would you choose? All right, so we have 6 markers to choose from. So here we see the acoustic velocity is about 1,400 feet per second. So when I go to this next slide, what I've done here is I've used the software to individually analyze this shot 6 times for each marker. And the reason that I wanted to do this was to show you, you can sort of see this acoustic velocity profile that's created by doing this. So if I were just to choose that very first mandrel that I saw and use that as my downhole marker, the software is going to calculate an acoustic velocity of 1,355 feet per second, and it's going to use that to calculate a fluid level depth of 7,003 feet. All right, so here's my liquid level right down here. So each marker that I choose, you can see here, as I'm getting closer to the liquid level, you see this trend here. The acoustic velocity is increasing. As the acoustic velocity is increasing, you're seeing that liquid level calculation increase as well. So this very last shot that you see here, where I've chosen to use that mandrel as my downhole marker that's closest to the liquid level, the acoustic velocity is 1,434 feet per second, and my liquid level calculation is just over 7,400 feet. So that's a 400-foot difference just by using a marker that's closer to the liquid level. For those of you that have wells where you're counting collars, it's the exact same situation. If you have a short collar count, that software is going to use the acoustic velocity at that collar to calculate your liquid level depth. So it's the same concept, no matter basically what type of well you're shooting fluid levels on, whether you're using the collar count or you're using the downhole marker. The closer you can get that point that you want the software to use to calculate your depth, the closer you can get to the liquid level, the more accurate that liquid level shot's going to be.
Carrie, I'd like to make a comment just real quick on that.
Yes, please.
The acoustic velocity here that you show on the chart is the average from the surface to that downhole marker. And so it's an average of that distance and time to calculate the average acoustic velocity for each interval. And that you don't have we're not using the acoustic velocity between each marker with this method.
Thank you, Lynn. All right, so this next fluid level shot is from a different instrument called the Model H. And I believe we have some Model H participants that are joining us today. So this Model H instrument, it basically has the same operating software as our TWM. All right, so here we have a fluid level shot on a Gaslift well. When we apply that low pass filter, now we're starting to see the reflection kick sort of pop out. With the Model H, it's very similar as far as being able to enter your Gaslift mandrels into the software. So this is a copy of a wellbore schematic, and so from that wellbore schematic, I entered the subsurface safety valve. There were 8 mandrels, and then this R for the Model H represents the packer. All right, so I have all of these downhole markers within the software. With the Model H, once you acquire the shot, you're going to see these markers, and I've gone over them just to make them a little bit more visible. But what you're seeing here is for each one of these markers that's placed, so they're placed separately all the way down to the fluid level, and then we do actually see this acoustic velocity profile being built. And so here we're actually looking at the acoustic velocity from the surface to the first marker, and then all the way in between the markers. So it's actually fine-tuning that acoustic velocity all the way down to the liquid level. And I know most of you aren't using the Model H software, but this is an excellent way for you to again, kind of visualize how the acoustic velocity is changing. One of the reasons this is really important, and it's important to pay attention to the acoustic velocity, as you're kind of working your way down, is that if the acoustic velocity is out of range, that's an indication that there's a problem. If you're working your way down that fluid level shot and you're placing markers, if you're coming along here and the the next marker you choose says it's 1,500 feet per second, that's going to be an indication that you've chosen a marker that is out of range. So you've chosen an incorrect marker for that particular analysis. All right, so if the acoustic velocity is out of range, in whatever circumstance, there's a problem, you need to go back and check that. So the acoustic velocity is important. Be aware of the acoustic velocity. It's great quality check to make sure that you've got the shot analyzed correctly, that you've got the correct marker, a good marker selected. It's a good check to verify your gaslit valves are spaced correctly. You're going to get better fluid level calculations. You know, it's important for accuracy. Of course, verify your gas gravity and uniform gas composition in the well. And again, we typically see that an increasing trend in the acoustic velocity as the depth of the wellbore increases because we're increasing temperature and pressure. All right, so that's going to impact the acoustic velocity. And so each particular gas has its own characteristics, and we do have several different charts for different types of gases. So if you want more information, whatever particular type of gases that you have, if you'll let us know, you know, we can get you some additional information on that. All right, so direction of kick. So the shape and the direction of the echoes across the valves depend on two basic factors. Number one, the physical characteristics of the mandrels, and number two, whether the operator is shooting down the tubing or the casing. So there's many different types of valves and mandrels are manufactured. The shape of the mandrel, as well as the space within the mandrel where the valve is located, is going to have an impact on the resulting acoustic echo. There's a big difference if you're using conventional versus side pocket mandrels because you have a larger profile, especially when you're shooting down the tubing. So on, shooting down the tubing casing annulus, whether it's conventional or side pocket, you have this profile sticking out here, so you are going to see a definite kick, when you're shooting down the tubing casing annulus. Shooting down the tubing, though, with the side pocket mandrel, that pressure wave is going to travel down and sort of increase to take up the area where that valve is located. With the conventional, you don't have that large of an area, so the kick's going to be a little bit smaller. Let's look at this little animation here. So a pressure wave traveling down the tubing is going to expand to fill the volume of area where the valve is located. So we see an upward kick generated on the acoustic trace. So here we see a shot down the tubing, and we see some nice big up kicks. Again, this is on a side pocket mandrel. All right, then down the tubing casing annulus, we're going to typically see a downward kick. So once that pressure wave is traveling down the casing, reaches the outside of the mandrel, which is taking up space, it has to contract to fit into that decreased cross-sectional area. And so down the casing, we typically see a down kick. All right, so here we have a shot down the casing. We see down kicks across each one of those mandrels. Now, one thing you can do once you have your tubing and casing shots is you can overlay them. So in the TAM software, if you go to the annotations button and click previous shots, and I have an example, we'll step through that here in just a bit. But you can choose to overlay the tubing and casing shots. And so you see the tubing shot here in black, and then the casing shot overlaid in blue. So there's a couple of reasons it's a good idea to overlay shots. Number one, we see do the mandrel reflections line up. Okay, so here we see the mandrels line up pretty nicely here. We see the up kicks for the tubing, the down kicks on the casing. They both line up nicely with the mandrels here. All right, and once we get everything lined up, kind of once we see what is supposed to be there, now we can see maybe what isn't supposed to be there. Do we see additional up kicks or down kicks? Anything that might indicate possible holes or restrictions or any other problems? All right, so this next example is a horizontal gas-lifted, plunger-lifted well. So stratified gas flow regimes exist in horizontal gas wells. So we're going to look at here a fluid level shot down the tubing casing annulus, and it shows the liquid level was at a depth of 9,287 feet. So the ability to see past the end of the tubing is unusual in a vertical plunger-lipped well because the liquid level is normally at the end of the tubing. In horizontal wells, though we see stratified flow exist, it's not uncommon to see the features in the well bore in the horizontal section past the end of the tubing. The horizontal section appears to be relatively dry, but a significant amount of liquid is still entering the tubing. Differential tubing and casing pressure don't indicate much liquid loading, but liquid exists in the horizontal and causes more liquid loading than expected. We received a call about this well. This gentleman said, I know I have a fluid level. I know I'm getting fluid where I'm getting production to surface, but when I shoot the fluid level, I'm seeing all the way down. Lynn and Ken, I believe, traveled up to shoot some additional fluid levels on this well. So we see some kicks here from the mandrels. We have the wellbore overlay, right? So we see a placement of the Gaslift valve. Here we can see the end of the tubing. We see some perforations. In the software, I entered you can enter the deviation survey, and then here's the approximate locations of where those Gaslift valves are located. And this is where the software was coming back and telling him there was a liquid level located. This is also that same screen in TAM. So if you wanted to enter a deviation survey, like we have an example I can step through with you guys. On that survey tab, if you have your deviation survey in Excel spreadsheet, you can essentially just copy and paste over those measured and true vertical depths. So the TAM software will show the wellbore deviation, and then it will also show you the placement of your Gaslift valves. So we have an animation here of what was happening on this particular well. So the fluid level was shot, so as that pressure wave is traveling down, it's reflecting off of those mandrels down the tubing casing annulus, and so we see each one of those appear as we're working our way down the wellbore. We see that last perforation. We see an upkick here. We see an upkick at the end of the tubing. All right, and then we're seeing some more perforated intervals here. And so what was actually happening, that pressure wave was traveling down, and when it got to the end of the tubing, rather than reflecting on the fluid that was there, that stratified flow, that means that the gas and the fluid are separated in the horizontal area. And so that pressure wave just traveled right on top of the fluid. And so what we're seeing as the liquid level here was just where that gas eventually hit, just sort of a liquid-filled trap. All right, so that's what was happening on this particular well. And so this is something that we have seen with horizontal wells. Lynn, do you have any additional comments on this one?
No, you did perfect. One of the more interesting things is when you look at after the end of the tubing, the upkicks you see match with the perforations.
So we're seeing here.
Yeah.
Here, yep.
Yeah. So that's
all the way down.
That's right.
Thanks, Lynn. All right, problems in the tubing string. So in general, if the lower valves are open or the orifice is open and fluids can move into the casing annulus without a check valve stopping backflow into the annulus, then the liquid level will raise to maintain equilibrium with the gas pressure in the annulus. In this case, the liquid level will rise to the level of the deepest active injection point. If liquid flow back into the annulus is checked, then the liquid level will be below the deepest injection point previously obtained. If there's a hole in the tubing, the liquid level in the annulus will rise to the hole in the tubing. So we're going to look at some examples here. This is an example using the Model H instrument. This is on a Gaslift well. All right, so here we see the reflections off of the mandrels here. And then there's one reflection here. We see a little upkick in between the first and second mandrels. So when you're kind of working your way down and you're identifying your Gaslift mandrels, you want to make sure that, in this particular instance, we see an upkick here between those two mandrels. But lots of times with so many Gaslift mandrels, and we see, 14 and 15 now in some wells, but we're going to see reflections off some of the mandrels as well. And so I'll work through a couple of those just to help you kind of work your way down, making sure that you're able to identify each reflection as either a mandrel or something physical in the well, or a repeat of something physical in the well, or something new. And so here, this was an upkick. It was not a repeat of anything that was previously in the well. And so this was a hole in the tubing. And so we can use our depth reference marker to identify the depth to that hole of 4,242 feet. All right, here's another example. We're seeing two shots here, and this is one of the examples that I have for you in the TAM examples. So it's titled Gaslift Hole in Tubing. So we see the first shot here is a tubing shot. We see it has a high fluid level. All right, so these are just repeats of that high liquid level. But you see sort of a suspect upkick at just past 1.5 seconds. So now we take a look at the shot down the casing. All right, so here we have our shot down the casing. We're seeing some mandrels identified with the reflections. Then again, we see that sort of suspect kick there near the beginning of the shot. So we want to overlay the shot. So how do you overlay the shots? I wanted to stick this in here real quick. So if you click on your annotations button, click on previous shots. We always call it a shot overlay, but if you're looking for it in the software, it's under previous shots. So click that previous shots button. That brings up your overlay selection. And then from there, you can turn the shots on or off. If you start overlaying more than 3 or 4, it gets start getting kind of jumbled. But anyway, this is how you go in and overlay those shots. So here we have that shot overlay. And by overlaying those shots, now we can see that hole at just past 1.5 seconds lines up on the tubing and casing. And so we can verify that that's a hole in the tubing. You can use your depth reference line. It's a really handy line that I use quite a bit. Use that depth reference line to slide over, and it tells us that that hole is located 1.5 seconds into the shot and at 1,083 feet. All right, tips and techniques. Do I have to turn a gas lift injection off before I shoot a fluid level? The answer is no, unless excessive noise prohibits you from getting an accurate liquid level analysis. So this is a fluid level shot where the gas lift injection is on, and I have this example for you guys in your examples folder. So we see lots of noise here. Apply that low pass filter, and yes, that cleans it up for us a bit. But if you look at that wellbore overlay, you're not really able to determine any kicks across the mandrels there. So it's hard to identify any details about the shot, but we do see the liquid level. So a case like this sort of depends on what you're looking for. If you just want a general idea where the liquid level's at, leave that injection on. You're not going to get a quality shot. You won't have a lot of detail. Trying to use acoustic velocity will be difficult because you're not going to have anything to really use as a downhole marker. But here's an example for you. You can certainly do that. So this is that same well with the gas lift injection turned off. And so we see the mandrels. There's our subsurface safety valve. We see the kicks across those mandrels. They're much more clearly identifiable. Other sources of background noise in gas lift installations include compressors, reciprocating pumps, and we've even seen this wave-induced vibrations in offshore platforms. I'm sure some of you guys have seen that too. How can I tell a quality fluid level shot has been acquired? Our go-to answer is take multiple shots. Take a second shot, take a third shot, take additional shots for comparison always. If the shot doesn't make sense, keep taking shots. Start making changes. Change the conditions. Keep taking shots until you understand. One of the problems that we see, if you only take one shot and you don't have another one to compare it to, something like this might occur. So here we have a fluid level shot that was taken, and you see there's a reflection kick here. The second shot it was taken, we're not seeing that kick. So which is the right one? Is one of these the fluid level? Was this a well analyzer and somebody stepped on the cable, when they walked by and it created this kick? It's always important to take more than one shot. If you take 2 shots and they're not the same, take a third shot. Keep taking shots until things make sense. Check for repeatability. Compare the acoustic velocity to what you know to expect. All right, acoustic velocity is a good quality check. Compare and overlay those shots. That way, it's going to help you identify anomalies. All right, so those are some acoustic velocity, take multiple shots. The 2 of the most important things that you can do to make sure that you've got a good quality shot to analyze. What are some troubleshooting techniques used in the industry to check integrity? So the following example illustrates the use of a complete fluid level analysis to validate the gas lift design, verify the artificial lift system is operating efficiently. This is one acoustic technique that a company used to search for holes and restrictions along the tubing string, as well as verify there's no pressure communication between the tubing and casing annulus. A total of 20 shots were taken over a period of 132 minutes. At the beginning of the test, an initial fluid level shot was taken along with tubing and casing pressure measurements. Then high pressure gas was injected into the tubing at the surface, and as that tubing pressure increased, the fluid level decreases, and so each one of those acoustic shots shows those mandrels as it's being uncovered. Once that fourth mandrel was uncovered, the tubing pressure continued to be increased, resulting in depressing that fluid level below the end of the tubing. So in that last shot, you see there below the end of the tubing. After observing the tubing was clear of any obstructions, the tubing pressure was bled off, allowed that fluid level to rise back to where that initial height was. Then the process was repeated again. And so here I'll show you this is just a graph. We like graphs here. So as that fluid level, as that pressure is increasing, the fluid level is decreasing. Here it is down below the end of the tubing. They bled that tubing pressure off, and then they went through the steps again. That process was repeated again. Gas was injected down the tubing, pushing that fluid level down. The casing pressure didn't change. The check valves held, and there was no pressure communication between the casing and tubing during this test. All right, can a leaky gas lift valve be detected with an acoustic shot? For a long time, our answer was basically no, but we've learned some new things, and so now we say yes using certain techniques. So I've got 3 different techniques that we've used. This first one here was one that Lynn Rowland did. This was a very high rate, high pressure gas lift well. They had a problem. The gas lift system wasn't working, so the well was shut in. After a few weeks, a liquid level was acquired on the well, and so due to the high pressure and the fact that the well was quiet, the gas lift mandrels it was really easy to see, to look at the reflections. You know, we had lots of detail across those gas lift mandrels and valves. And so it was pretty easy to, go in and study each one, and the problem valve was identified because it's the one that looked different. So it did require some study of each valve echo. And again, the conditions were such that it was very quiet and high pressure. So you were able to see a lot more detail. In this example, the damaged valves actually showed up during the fluid level shot. So if the unloading valve, or if a valve has some type of physical damage and the echo is different, then you'll see it. However, if the internal parts of the valve are the same, there's a pressure seal at the valve, the echo at the valve will be the same and no difference will be seen. If the pressure seal fails, it's likely the echo at the valve will show a strange kick, and you may be able to identify a valve with a problem. All right, so here's 2 fluid level shots. This was on the same well. This top one here was from October 27th. All right, and so there was a kick here that appeared to be located at the depth of this valve. And then a month later, they took another fluid level shot. And again, we're seeing it was just a damaged valve, so we're able to see that pretty easily. The third method that we have is the dual shot method. So the dual shot method identifies communication between the tubing and casing using 2 gas guns. So let's kind of talk through how this works. So here you see a picture of this well, and we've got a remote fire gas gun on the tubing, and you see a compact gas gun on the casing. So to look for communication between the tubing and casing, we're going to shoot down the tubing and simultaneously listen on the casing. All right, so this is our fire gun. We're going to shoot down the tubing, and we're only going to listen with the casing gun. So the way that happens is we fire the tubing gas gun to send a pressure wave down the tubing, unplug the tubing microphone cable from the well analyzer. You'll see that this is using the well analyzer. You're going to unplug the tubing microphone cable from a T after the shot is fired. Leave the casing microphone cable plugged into the well analyzer. The acoustic signal is created in the tubing, holes, malfunctioning check valves, malfunctioning gas lift valves are going to pass that pressure wave into the casing. Once you shoot that pressure wave, it characteristically wants to expand. And so it's going to expand through, and so we're able to identify any pressure communication. For calculating the depth on the listen gun, we use the average acoustic velocity of the tubing and casing shots, the shots that we took prior to shooting the dual shot. All right, so let's kind of step through this a little better. So here is the well analyzer. Here you've got the well analyzer, and there's a T here. And so hooked up to the T, you've got the microphone cable from the remote fire gun and the microphone cable from the compact gas gun. So as soon as that fluid level is shot, you're going to unplug the gun microphone cable. We just want the software to know that the shot has been fired. That's the whole purpose of leaving that plugged in and then immediately unplugging that. Here's an animation. So the fluid is displaced out of the tubing down to the operating valve. The shot's fired using the remote fire gun and then immediately unplugged. That microphone cable is disconnected. So now that pressure wave is traveling down the tubing, and any possible pressure communication point, you see that wave pass through, and then it shows up on the casing gun, which is just listening. All right, we're only using the microphone on that, on the casing gun. So this is one of the results. This is the dual shot on this particular well. And so here we see there's pressure communication right here at this 8th valve. All right, so if there was no pressure communication, then we would just see nothing but noise here for this compact gas gun. So before the dual shot is taken, it's important to shoot a fluid level down the casing and shoot a fluid level down the tubing. It's important that you analyze both of those shots, make sure that you have an accurate fluid level depth and an accurate acoustic velocity for each one of those. So here you see the dual shot. All right, so this is the dual shot here in black, and we have the casing shot overlaid. All right, so here's that casing shot, and so you see the kicks from those mandrels, and then right here at mandrel 8, this is where we see communication. So here's another example. Here's the tubing shot, and then the casing shot. So both of these were taken before the dual shot. And so now with the dual shot here we see communication. Shooting down the tubing or shooting down the casing, you know, lots of times you see a difference in acoustic velocity. You see a difference in pressure and temperature, and you see a difference in acoustic velocity. And so we've got a shot that's traveling down the tubing. You know, it's traveling through one medium and then traveling up another medium. And so if we are shooting down the tubing, but we're analyzing the shot on the casing, you know, it's traveling down at one speed and then traveling back at another. So the way to account for that is to use the acoustic velocity from those shots that you initially analyzed, and you're going to add them together and basically take an average acoustic velocity of the tubing and casing shots. And so you're going to use that acoustic velocity on this dual shot. You're going to use the acoustic velocity method to analyze the shot, and you're going to manually enter that average acoustic velocity between those two. All right, and so that's going to give you the depth, and then you're able to use that wellbore overlay, and that calculated depth now is going to line up to that particular malfunctioning valve or leaky valve. All right, here's another shot. This is just another example. Here we see sort of a close-up to it, but we have the tubing shot and the casing shots that were taken prior to the dual shot. All right, so here's the dual shot. And one thing that if you do try these, or if you have, that you will see is once you get down to the fluid level, you do see characteristics from both the tubing and the casing, right? Because now we have a way for that reflection that's going to pass back through. So it can sometimes get a little messy if you're looking down past the liquid level. So it's basically just you're looking from where the shot is fired to where that liquid level's at. That's where you're looking for that pressure communication. So for our wireless equipment operators, because of the wireless equipment, you've got a particular channel. You have two channels coming off of each gun, one for pressure and one for acoustic. All right, and that's coming into your base station. And your base station is only able to get those two channels for your fluid level shot. So there's no way to perform this using one base station and two guns. That's just because the base station with the fluid level shot is not able to accept the four channels that would be coming through, four channels of data for two different guns. We do have a feature called plunger tracking. Using that plunger lift application, it's able to simultaneously acquire four channels of data. All right, so you can see here we've got our wireless equipment hooked up to this well. Here you see a 1500 PSI gun along with a 5K gun. And typically the results are going to be better if you're using the same gun, because the microphone on that 5K gun is a little bit more rigid, so you're not going to get as much detail. All right, so using the same type of gun when you're overlaying everything is going to be a little bit better for you. You're going to have better results, better comparison. All right, so using the TAM application, you can get everything up and go ahead and start acquiring the data. Press the fire shot button on your tubing gun, and we're listening for the pass-through echo on the casing gun. So here's an example here. This is the plunger lift or the plunger tracking module within TAM. And so essentially you would just start acquiring. What you see here is data that's streaming. You see the two channels from the tubing gun and two channels from the casing gun, and so it's streaming data. Then you walk over and press the fire shot button to create the shot. And so once that fire shot button is pressed, then it's going to fire the shot. And now you're going to be able to see, you'll have to compare the tubing and casing guns, and you have some annotation options that you can use with the plunger lift module here. So you can use the annotations to locate where that shot was fired. Here we see an annotation to locate the upkick at the end of the tubing. And then annotation 3 locates the liquid level. All right, so it does take a little bit more work manually if you have the wireless equipment and you're using the plunger tracking feature to perform your dual shot. There's a zoom feature where you can go in and just specifically highlight that fluid level shot. So there are some tips and things that we can help you out getting that dual shot analyzed. All right, so here you just see a close-up of the dual shot here.
Yeah, when you shoot the fluid level with plunger lift, you have two guns acquiring data, but you need to set the sampling speed to 1,000 hertz. You have to change the default sampling speed is 30 hertz. If you're going to do a dual shot, you're going to want to see the same high-speed acoustic data. And so make sure you sample at 1,000 hertz. And that's on the, go back one slide, Carrie. I think it's not there, back one more. Right there. So there at the upper right-hand corner, it shows that the sampling rate's 1,000 hertz, and you need to select that before you start the test. So that's important. And the reason why, if you go back to those two, the two shots, this one we put the annotations on the screen on the tubing shot, and then the next one we still see the same annotations. Go forward one slide here. Those annotations A2, A3 are still from the previous slide, and there shouldn't be any noise on this channel because there was no shot fired. And so this shows that on the casing acoustic, it heard a signal pass through a valve, and that meant there's communication through a specific valve. And the A2 and A3 were the annotations from the tubing shot, and it just shows the signals pass through. And the reason why we have to use the average acoustic velocity is because the shot goes down the tubing and then back up the casing, and so that means you have to have both the acoustic velocity on the tubing and the acoustic velocity on the casing average to get the right distance for the round trip travel time shown on the dual shot. But this is just what you look for. You look for communication on the gun that you're listening on. And if you see noise there, then it came from a bad check or a bad valve.
All right, so beneficial information is obtained throughout the life of a gas lift well. Knowing the acoustic velocity profile of a well is going to help you make sure you've got a good quality shot. It's going to help make sure that you've got accurate fluid level shot, also just to verify your gas composition. Identifying reflection kicks across valves and mandrels result in a more accurate depth analysis. Operating valves are quickly and easily identified, especially using TAM and that wellbore overlay. All right. So I hope you've picked up some good tips here, and I'll go through some examples here in just a bit. But right now, we'd like to open up and see if you guys have any questions so far.
Yes, so we actually have a few questions here, Carrie Ann, if you want to cover that before jumping into the examples.
Yes, absolutely.
And let's start with Bill from ConocoPhillips have been participating actively today, and he has kind of a long question comment. Say, is it reasonable for me to build the temperature profile using my acoustic velocity if should is during during injecting or shortly after I finish injecting? Initially, it has some bullets here. Is A, could I predict my temperature profile without spending the money on wireline? And B, could I troubleshoot a valve being hung open connected to a temperature problem rather than a valve being failed?
You want me to try to answer that, Carrie Ann?
Sure. Hi, Bill.
Hey, guys.
There's two temperature profiles. There's a temperature profile in the casing, which is we typically see that, and then there's a producing temperature profile in the tubing, where the producing fluids control the temperature in the tubing. So a fluid level shot is down the casing is going to typically be based on the geothermal temperature gradient of the earth, and that pretty much controls the temperature profile, the earth temperature in the casing. It may be a little bit higher if you're producing liquids. So if you have the known depth to each gas lift valve, and you calculate the acoustic velocity between each gas lift valve, then you can go to the plot of the acoustic velocity versus temperature and plot those pressure. And so yes, you could find an abnormal acoustic velocity as long as you could easily identify each of the gas lift valves, and that acoustic velocity would be abnormal because there would be a temperature leak or temperature change that wasn't linear based on depth. So, but right now what TAM does, it doesn't do the acoustic velocity between each valve. It does the average from the surface to the downhole marker. And we would want to have the method that the Model H has that does the acoustic velocity between each valve. And then you'd be able to see the individual acoustic velocities versus between each valve depth. And then you could compare that to what it should be based on pressure and temperature. So yeah, basically it'd take a little bit of work. It'd take a lot of knowledge about the well, take a detailed knowledge about the geothermal temperature profile. Some wells may not have uniform temperature profiles versus depth, so it'd be interesting to try to figure that out, but you probably could.
So yeah, let me just kind of, that's one of my other lower questions was, I was wondering if TAM had that same, because we've got both, right? We've got some Model H and we got TAM, and I wondered if they also had that bucket that kind of showed velocity versus, at different points during the well, but it sounds like it doesn't. I think I can calculate it without too much trouble, right? Because I could just do the difference.
Yeah, you can do it yourself. But
here's my strategic kind of problem that I have is that, so after a well's been shut in, and this happens to us a lot in the Permian, A well that is shut in has a dramatically different temperature profile than once it starts flowing. And a lot of times, so we will have wells where the static surface temperature, say it's 70 degrees, it'll eventually meet the flowing gradient, but the flowing gradient might have a surface temperature of 170 or 130 degrees or 140 degrees.
Right.
And the problem that we get into, as you can imagine, is what do they design the gas lift design to, right? And because the valves are so sensitive to temperature, someone probably designs it closer to the flowing one than the static one. So sometimes when we're troubleshooting and we've got gas that's circulating, we're really trying to establish an answer of, is there something wrong with that valve? And we can get that off the dual shot, right? We can find out if we've got gas coming around or not. But then the question becomes, if we could get the well flowing and get it to warm up, would that valve likely close? And that's the thing I'm trying to work my way through it.
Yeah, we just need to talk some more, maybe offline.
Okay, yeah, that sounds awesome. I'd like to do that. And then my only other one that I had before I get off of it is does anyone ever do the dual shot down the casing and measure the tubing? Because I think you're talking mostly about down the tubing and measuring the acoustics on the casing for your dual shots. Does anybody ever do it the other way around?
Well, when we did it, when Shay Providence from, it was Apache, yeah, that we did that with, he said he always does it both ways. So yeah, we usually do shots both sides. And sometimes you see something different when you shoot down the casing versus shooting down the tubing.
That's why I'm bringing it up. Sometimes the answer gets a little more clear if you do both, because one way might just be a check valve leaking, and the other one might be a valve failed, and sometimes you can differentiate. That's the reason I asked.
That's right. And so the main thing he said to do was that, you find a well that's not working and producing as it should be, and the operator alerts him, and the operator first goes to the well and drives the liquid and tubing down the tubing. It doesn't change the casing conditions at all. And then he starts shooting down the dual shot when he gets there, once liquid level is down past the operating valve. So the pressure in the casing is a lot higher than the pressure in the tubing, and I was surprised it would work, but it doesn't seem to matter. He said he tries really hard to maintain a similar pressure profile, even though he pushes the liquid out in the tubing, and not change the conditions in the casing.
And I believe he said he'd shut him in if he knew he was going to do the dual shot the next day. Shut it in the night before.
Yeah, when we went there, he just said he called the tech in the morning, and they pushed it down before he got there.
We're trying to do stuff as close to live conditions as we can because of that temperature thing I was talking about a minute ago.
Yeah.
Still, so I was just curious.
I'll be glad to help you on that if you'd like.
Okay, yeah, awesome. Thank you. This is really good. Thank you very much.
Thanks, Bill.
We have some other questions, and we have here a few more questions saying, how do you know the bottom hole temperature? And that was when we were in slide number 16 about that early.
Well, normally when you drill a well, that you have a pressure, an initial pressure, initial temperature, and the Earth's temperature pretty much stays constant at the bottom of the well. You don't really see a change in it. So what we assume is that you enter the bottom hole temperature from when it's drilled, and you enter the surface temperature that's close to the mean annual temperature of the surface, and that's your surface temperature. So that's what we typically enter into the program. But sometimes someone will do a static pressure temperature survey in a well, especially a gas lift well. They'll do static and flowing surveys. So.
Well, Lupe has a question, kind of a common question, and many users asking, does the amount of pressure in the shot or pressurizing the gun make a difference on the velocity?
No, the pressure, more pressure makes bigger echoes. So when you charge a gun to as high pressure as possible, let's say you have the remote fire gas gun, and the maximum pressure you can have in that gun is 1,500 pounds of pressure, and let's say the casing pressure is 700 psi. So you you've got about 800 psi differential pressure. That's going to make the echoes as big as it can possibly be with the remote fire gas gun. If you use less differential pressure, the round trip travel time will be exactly the same. It won't make the composition of the gas change. It won't make the pressure of the gas or the temperature of the gas change. It's just going to make a smaller energy pressure wave. So the echo from the pressure wave will be smaller as differential pressure decreases, and that's all that happens.
Okay, thanks. We have a question. It's asking how to detect a leaky non-return valve. It's kind of a check valve in casing. This person has a Gaslift Mandrel, but they are using a casing check valve, and he's asking how to detect it is leaking.
Well, that's what the purpose of dual shot was, because on a dual shot you have the casing with the check valve on the outside, and the check valve is supposed to hold the pressure in the casing annulus if there's a packer. And so when the check valve is failed or is not checking, and you shoot a fluid level down the tubing, the pressure wave will pass through the check valve and show up as a signal on the casing. So we would normally say in the past you can't see a leaky valve or a leaky check, because if you just shoot down one side of it, it's just going to show an echo, and it's not going to show a hole. It's just going to be a normal echo, like the valve is still intact. The only time you see something, Carrie-Ann said, if the valve's washed out, you'll see or a hole, you'll see those, but you won't see a leaky check. So the dual shot method is what lets us see that, because the check will open and pass through the pressure wave from the shot.
Okay. Carrie-Ann, we have a couple of more questions before you go to the samples. And
that's great.
One question is how we identify, I know you already covered part of this, but the question is how we identify Gaslift valve leakage through casing head pressure and tubing head pressure. And usually that's not covered on the options that we have to identify leaky valve. We have some other options that we already covered.
Well, when we shoot the fluid level, we measure the pressure buildup. And so anytime that you have the pressure buildup is measured for up to 15 minutes. So anytime you shoot the fluid level, if you're losing pressure and it's supposed to be held, then after you shoot the fluid level, the pressure buildup test will show a decrease or drop in pressure. So you can see for 15 minutes the pressure measurement at a 5-second interval from the fluid level shot. So on TAM, shooting a fluid level, you'll see liquid level or you'll see the operating valve. But if you keep on measuring the pressure, you can see that the pressure is leaking off. So just look at the casing pressure buildup curve.
Okay, and a last question before going to examples is, what pressure is needed in the acoustic velocity calculation? If you have the input gas shut off, the pressure would decrease in casing annulus. Does the wave travel faster or slower?
So Carrie-Ann has a plot of that. If you go back, Carrie-Ann, can you go to that plot that shows acoustic velocity versus pressure and temperature?
Yes.
Okay, so if the pressure is going at 1,000 pounds in the casing, and the pressure's leaking off towards zero, then all those curves that are less than 190 degrees Fahrenheit show that as the pressure drops from 1,000 towards zero, that the acoustic velocity goes up. So you can put your mouse on it, Carrie-Ann, if you want, to just show that as you're moving from the right to the left, the acoustic velocity horizontally is going up. So you follow a temperature line, temperature's not changing, and you go along that line, the blue line, from 1,000 psi to zero. Then as the pressure drops, the acoustic velocity increases.
Yeah.
Yeah.
Okay, that's all we have so far, Carrie-Ann. You can now work on the examples.
Okay, I did see one question here. I was trying to look through the the chat too to see if there were any additional questions. And there was one here from Joshua asking, are we looking for the valve closest above or below the fluid level? And we're looking for the valve that's closest to the fluid, above the fluid level. So typically once we see the fluid level, we're not going to see past that. So you're going to find the closest mandrel or valve above the fluid level. So if that wasn't specifically your question, Joshua, please let me know. All right. So let's look at some examples here. If you're looking through the examples with me, and once you've imported them, if you click on Pick Well, you're going to see this Ask Echometer Gaslift group, and then you'll see the list of examples below that. So let's start here with multiple kicks 1. This is a really good way just to exercise working your way down. If you have multiple kicks here, it's pretty easy to see, where these first ones line up. And as we get closer to the liquid level, it might be, the more reflections you have, the closer the valves are. It might be a little more difficult to figure out which reflection goes with the mandrel. So one of the things that I do is I like to start, once I get the Gaslift valves entered, I start at the very top valve, and I just kind of start working my way down. So you can see here the software first tried to analyze this using the collar count method, and it's not getting anywhere with that. So I'm going to click downhole markers. And so when I click downhole markers, I can start all the way up here to the very top valve. All right. I'll just do this sort of quickly. But you can see as each one of these is placed, you can watch as the rest of the valves, everything else is adjusting, and it's adjusting according to the acoustic velocity that it's calculating at that valve. Right, so if I move down to this one, and so I'm placing it up here, or you have this window down here, but you can fine tune it a little more clearly. All right, see here we've got a reflection here, so if you're working your way down.
Carrie Ann, show over on the side that the gun's attached to the tubing.
Okay, here.
And the kicks are up, not down.
So Tim will tell you if you let the software know whether you're shooting down the tubing or the casing. So here we see this as a shot down the tubing. So we see the gun with the arrow on the tubing side. And then, as Lynn mentioned, these are up kicks, so we're shooting down the tubing. So on this marker here, so if I line this up and I see that the acoustic velocity is 1,158 feet per second, and I go to the next one, we'll see that it's going to adjust a little bit. But you see there's 2 reflection kicks here. So if I were to pick this first kick, all of a sudden it jumps up to 1,200 feet per second. And it's been a lot less working my way down. So I go to the reflection, and now it makes more sense. It's more in line with the acoustic velocity and the trend that we're kind of seeing. All right, so this is one way that that you can use just to make sure that you're looking at the right kick as you're kind of working your way down. So if you have a lot of mandrels, you might initially think it's going to make it really difficult, and actually it's, if you use this method and just kind of work your way down, you can get as close as you can. It's going to help you make sure that you're picking the right mandrel, picking the right reflection. That's going to give you a lot more accurate fluid level. And I realize a lot of people say, well, there's no need to get, if all you're wanting to know is which valve the fluid level is closest to, then that's good. One of the things that we want to teach you is accuracy and how you're going to get the most accurate results.
Carrie Ann, would you address what kick is at about 7 seconds and what's about at 9.5 seconds? What are those?
All right, so here, let's get out of this. All right, so if you see reflection kicks here, you know, this one is kind of shown up in the middle. So I'm wondering, is this going to be my next valve, or is this maybe a repeat? So I go into my annotations and I turn on my depth reference line. I'll pull that down here. So I start looking at time intervals. I use time intervals. So if let me get a piece of paper here and a pencil. All right, so if my time to that first kick is 3.4 seconds, the time to my second kick is 5.92 seconds. So I can turn on I need to see my calculator. TAM and calculator. There we go. All right, so I can say, okay, there's 5.920 minus 3.423. Okay, so the difference between these two is 2.497 seconds. All right, so the easiest thing to do is take the distance to that first and double it. And that's 6.846 seconds. So if I come over here, 6.846 seconds. All right, that's pretty close. So this tells me that this kick I'm seeing here is a reflection off of that first valve. All right. I have another example we can kind of work through showing that too. One of the nice things about taking the time, sometimes, you know, it might take you 30 minutes to go through and analyze a shot and to get your calculator and your piece of paper out and to verify what's physically there and what's a reflection. But if you spend the time and analyze that shot, you're always going to have that one to refer back to. It's going to save you a lot of time in the future if you just take the time to understand those reflections and know what to look for. So let's go to the second one here. So if I go to multiple kicks 2. All right, so here I have a Gaslift shot that doesn't have any mandrels. So I need to come over here and I've got my Excel spreadsheet. So there's 2 places that you can enter mandrels. And so a lot of you, if you're importing a shot from TWM into TAM, with TWM, you're only able to enter 1 downhole marker. So out of your 13 mandrels, you're only able to enter 1. And so when you pull everything into TAM, you're still going to have to go in and fill in the rest of that information. All right, so if I've got so much stuff going on here. Okay, so I can, if you look over at the wellbore illustration over here to the left-hand side, there's a Gaslift valve and a question mark. So it knows that it's a Gaslift valve. So if I click the edit button here and open up my well file and go to lift system, it knows it's a Gaslift well because I've imported it from TWM. So I can click on this Gaslift valve with the question mark, and now I have the ability to manually enter the valves. The problem with using this particular method to enter those valve depths is it only gives you 10 spaces, and it doesn't give you the ability to add in additional lines. So the easiest thing to do is to click edit, go back into the well file. There's quick view, and then there's a detailed view. Okay, so quick view, there we have just our 10 that we could enter. Detailed view, now I can go into my lift system.
So you just copied the Excel
So
file.
I'm copying from the Excel spreadsheet. I'm going to click copy. And I'm going to come over here and click paste. Okay.
Good job.
Unfortunately, it only gave me 10. right? So you're going to have to still go in and add those additional rows, all right? And so now there we've got 11, 12, and 13 that we need to add. Or you can just manually enter them. All right, so I'm going to save that. Now on this well, we also have a survey that we can enter. Okay, so if I go back over here to my spreadsheet, okay, and you guys have this too, if you click on the wellbore deviation tab at the bottom, and I'm going to come over here to survey in my well file. And so you've got two columns here, one for measured depth and then one for true vertical depth. So you can copy and paste them individually, or you can even, I'm going to just copy both columns over to make it faster. But one thing I want to show you is if you have your deviation surveys in an Excel spreadsheet, you might have to do a little bit of cleanup. So if you've got, so if you've got, different headers or something like that, or for some reason you have spaces in between your rows there, you might need to go in and clean that up. If you have commas denoting, your hundreds and thousands, the commas are going to cause, when you copy and paste that over, the TAM is going to see that, if you have 3,423, you're going to see the 3 in the first column and the 423 in the second column, right? So that it thinks the comma is telling you to put it in another column. So if you go through, I'm sure you guys know how to do this. If you go to Format Cells and, just make sure that you don't have commas in there, just click on General, that's fine. So now we can go in and highlight the two columns. So we've got measure depth and true vertical depth. So I'm going to copy this. I'm going to paste them over here. Okay, so now that I've done that, now I'm able to see that wellbore deviation, and I'm able to see the location of each one of my valves. Okay, so I can save that. So now over here on my wellbore illustration on the left-hand side, and then you can see my wellbore overlay here. Now I've got my valves all showing up here, and I also have my fluid level with respect to the valves. Down at the bottom, on any well that you enter the deviation survey, you're going to see this little icon show up here, right, way over here on the bottom left-hand side. All right, so if you could just, yes.
A quick comment that as we have users all over the world, it's worth it to say that as any other value, you got to be careful on the unit where you have the survey from. So sometimes you can get some confusions between meters and foot. So just a quick comment on that. We've seen some people inputting the wrong unit, and that will for sure lead to a wrong calculation of the TVDs.
Oh, definitely. Thank you, Gustavo. All right. So now we have our gas lift valves entered. We've got our deviation survey here. For those of you that are brand new to the software, you do have some zooming abilities here. If you click on the zoom button over here, this gives you the ability to, this cursor is huge. Well, it's not going to let me. I'll use it from here. So there's a couple of plot controls. This echo zoom, it sort of highlights everything from the beginning of the shot to where your fluid level's at. Okay, so if you open up a shot where it just, maybe you're only seeing the beginning of the shot here, especially if it's defaulted to wrong fluid level, something like that, you can click that echo zoom or zoom all. It's going to take you all the way back out. There's also a select button. If you wanted to come in and take a closer look at a certain area, you can do that. And then we can zoom that back out. Okay, so with this shot, so now we've got our multiple kicks here. So this is another one where I can go in on my downhole markers. Oh, Tam. All right. Okay. So I can start here at my first valve.
And notice that this is these are down kicks and we're shooting down the casing.
Yes, thank you.
How the acoustic velocity is increasing every time you correct the kick from the mandrel.
All right. So this is another one here. Sometimes it gets, once you get closer to the liquid level and you start to see more reflections and things, it can get a little bit tricky. All right, and if that's the closest valve you can get to, that's fine too. But sometimes it just takes taking your time, getting your calculator out. This is another one though, that you can see we come along, and as we were lining up the reflections, there was also, you could see there was a change in the cross-sectional area for the production casing. I don't know if you guys saw that as we were kind of working our way down. And so there's a marker there for that, and then you can also see that on the wellbore schematic, on that wellbore overlay. All right, so any change in cross-sectional area that you see on a wellbore schematic is going to cause a reflection kick to come back. So anything can be used. And so you want to make sure, whether it's, you know, a production casing. I saw someone ask a question about a liner. Yes, if the liner is gonna show up, and a lot of times the liner is a bigger kick than the fluid level. You know, because there's a lot of energy that's still coming off the shot. The liner is a little bit higher up, so you know you'll see a big kick off the liner, and it takes a lot of energy. So yes, liners, tubing anchors, any change in cross-sectional area is going to cause a reflection, and it's something that you'll be able to physically see when you shoot that fluid level. Any other questions so far?
Yes, we had, well, I think you already covered that. You catch it from the chat, that question on the tune marker. But we had a question from, it's related to the dual shot technique also.
Okay.
It's on the dual shot. Do you need to shut off the injection right before shot, or better to leave down for a period of time?
I think with the idea is that you want to make sure that as many valves are uncovered as possible. Correct, Lynn?
Well, that's right. And so when you're shooting down the casing and the gas injection is on, then the gas valves are noisy and the gas compressor's noisy, and so there's more noise on the acoustic trace. So if you shut the valve to the compressor, that isolates the gas injection noise and the compressor noise, but you still will hear valve noise downhole. So I would try shooting it without shutting anything in at all. And if then I use low pass filter, and I can see my Gaslift mandrels and my liquid level, then I wouldn't shut the well in at all. The only time I shut the well in to shoot this fluid level is if I couldn't filter out the high frequency noise. So that would be my answer to the question.
Any other questions so far?
Yes, we have another question related to the liner, and Fadi is asking if we can measure the fluid level below the liner. I think you already said that before, but go ahead and confirm it.
there's three examples on from the example file for that one. And there's one that's called a PFL liner anchor that shows it. Which you see a tubing anchor kick, and you see a liner top kick, and a liquid level at the end of the tubing. So that's a good example of showing a liner, and it shows a smaller ID.
Okay. So for those of you that are asking about the liners and multiple kicks, there's some excellent examples in here with multiple kicks. They're pretty difficult shots.
But they go along with the presentation that was recorded. So you can.
Yes, that's right. That's right. So you can, watch the pre-recorded presentation, and then you can step through the examples that way. Okay. So when you import a TAM file, down here at the bottom, so this tells me I'm importing 14 wells, 80 total tests. So that's one of the reasons it took so long. That there's a lot of dynamometer tests. This is power. VT is valve test, counterbalance effect test, and plunger lift tests. So all of these are available from session 1 that you can import. So if I come over here and type in
It's PFL
tubing anchor liner.
Right. So if you look at the shot, this well has a 6,000 foot deep liner. The liner starts at 6,000 feet, and you can see the tubing anchor. Yeah, there you go. Good.
So there's the tubing anchor, down kick at the tubing anchor, and then you see a down kick at the liner.
Right, and then
there's the liquid.
You can also see an
maybe
up
like
kick.
a little up kick.
Yeah, so if you go equal time past the liquid level, you'll see an up kick from the liner. So when the pressure wave goes back out the liner, it shows up as an up kick. And the up kick's about 13.75 seconds.
So we do typically say that anything, you can't see past the liquid level. And so one of the things that you can do, there's a couple of other features here with the annotations. If we did full trace. So no, it's not that big of a kick, but you can use your depth reference line too. And so if this was your liner kick, so the time from the liner kick to the liquid level, and then add that time again, then you're going to see this up kick here, which is the up kick of the pressure wave traveling back out of the liner. So you see a down kick on the liner when it comes in, and you see an up kick as it's leaving the liner because that change in cross-sectional area. That's a really good example. I'm glad we found that, Lynn. Thank you.
You're welcome.
Carrie, I have one more question on that well that you had before, the Gaslift well, the multiple kicks too.
Yes.
And why is the echo at 13.8 seconds much larger than the other echoes? It's number 2. Yeah. You see the Mandrel echo at 13.8. It's way much bigger than the rest of the Mandrel's echoes.
We can probably, so if I turn on my, what did we say it was here? 3.245 seconds maybe. If you've got multiple kicks or you've got repeats of those reflections, and the amplitude of the wave of, if you have something physical in the well and you have a repeat right on top of that, it's going to increase the amplitude of that wave. Or if you have, a down kick from a liner or a tubing anchor and you have a hole in the tubing further up, that's an up kick. Maybe that repeat of the up kick happens still at the same time as a down kick. it's going to decrease the amplitude. So just keep that in mind. And that's a great question and something that you definitely want to make sure that you verify. So that gas lift hole in tubing, if you click on this liquid level history, it shows you what shots you have here. So we have 2 casing shots, and there's first, second, third shot tubing. So we have 2 casing shots and 3 tubing shots. And as Lynn pointed out, you can tell over here on this little wellbore illustration whether you're shooting down the tubing or the casing. All right, so this tubing shot here, we've got a high fluid level, and so we see that liquid level repeat. So this is where we had that suspect hole. So this was the example that we used. So if I want to go look at, let's go take a look at one of the casing shots real quick. Okay, so here's the casing shot. And so we see the hole right here. This is another example too where you've got some reflection kicks lining up, and then we have a reflection here that's not lined up with a mandrel. Minimize that. I'm going to turn on my depth reference line. And so I do have this in the examples for you. It says determine whether the kick is a hole or problem area, or is it just a repeat. And so here, if you look at the time to that first kick is 2.25 seconds. The time to the second kick is 3.704 seconds. So the difference between the two is 1.452 seconds. So if I take the 3.704, and I add the 1.452, then I get 5.156. So I can move this over here. All right, so I know that this kick is a repeat here. All right, so we have this kick here, this valve, and so the distance here is the same as the distance here. So this particular kick is a repeat. And so if you get shots like this and you want some help analyzing them, please feel free to send us your data and make sure that you send us a wellbore schematic. We'll be happy to kind of help analyze any difficult shots, and then that way you'll have this one well-analyzed shot that you'll be able to compare to future shots. Any other questions?
We have a question that's not related exactly to the liquid level analysis from Hector. He's asking if we have a chart that shows the chamber pressure in the gas gun compared to the tubing or casing pressure. I think it's referring to the differential pressure that we need to have across the gas gun and the surface pressure in the well, whatever we're shooting the fluid level.
You know, that's a good question, but it's really somewhat depth dependent, because if you have, let's say the chart says for a casing pressure of 85 psi, you need to use 400 psi charge pressure. Well, that's only true if the well's 5,000 foot deep. If the well's 10,000 foot deep, you probably need to use, maybe 800 pounds of pressure. So it's not only a chart of differential pressure, but it's a chart for casing pressure and charge pressure, but it also is depth related. So, and then also restriction related. If you have a liner at 8,000 foot in your well, and you got to shoot down to 10,000 feet, then you got to use more pressure to get past the liner, because the liner removes some of the energy from the traveling wave. So it's a complicated. It's best to just have experience for your wells and learn how much charge pressure gives you the best results.
Yes, we always say the good start point is 150 to 200 psi above the surface pressure, either tubing or casing, but that will always depend on the acoustic response that you have. How deep is the fluid level? For shallow fluid levels, usually you need a smaller amount of pressure, and for deeper wells, then the differential pressure that you might need might be much higher. So it will be based on the acoustic response that you have based well by well.
All right, Carrie Ann, you want to wrap her up?
All
Yes,
right.
we're gonna wrap it up with that. That's all the questions we have. Thank you very much.
Okay. Well, we really appreciate you all joining us today. We really enjoy bringing you guys these sessions, and please let us know if you have particular topics that you're needing to see. If you have any questions or follow-up questions, or if you're wanting any additional documentation, if you'd like copies of those papers, please email me and let me know. I'll be happy to send you whatever information you need. Again, thank you for joining us, and you guys have a great week, and we will see you next Wednesday.
Thanks, Carrie Ann.